So welcome back, everyone. Before we start, let me just say hello to our guests. We have visitors today, again from high school, I think, who want to figure out how it is at the university. So potential future students, if I don't scare them away with my talk here, I will try my best. I'll try my best not to scare you away. So we want to look into shading now. Again, into shading. We already did this in the third lecture, but of course shading is very important, so it makes sense to repeat it. And also we learned a lot of things in the meantime which are probably new, or which you didn't understand completely when we talked about it the first time. So I will repeat a lot of the things now, but yeah, take this also as an opportunity to repeat, because you also realize that a lot of the second exam will cover the lectures 6 to 12, so the ones that's not covered in the first lectures, in the first exam. But of course, you see that we need all this stuff that we had in the first 5 lectures as well, like implicit equations and things like that, and normal vector calculation. So yeah, we want to look into shading, and this is just a copy-paste from one of the slides that we had when we, from I think the texture mapping lecture, where we already talked about this, that we can, if we have the colors at the edges, so we have C1, C2, C3, and I write this as a vector now, because we have, of course, 3 values for each, which is a red, a green, and a blue value, RGB values. And then we can interpolate these vectors along the lines, and we can interpolate between the edges, between the values on the edges. So we can also do the interpolation here and here. And you already did this, you know this already from the very first practical assignment. And like I said, this is an image that we have seen before, but now at that time I said we will in a later lecture talk about how we do this efficiently, and this later is today, because now we know that, of course you guessed it, that we would draw the image rather like that, which is the scanline. So we use the scanline algorithm for this. We take the value, the color values, for example C1 here and C2 here, and then we move along the scanline. So we calculate here the delta R, delta G, and delta B value, and then we add them for each step of our scan line. We add them to the values before, and that way we can color the edges here. And of course we can also do this in this direction then, so we have to calculate 3 other values, R, G, and B, and add them to this color value here till we reach this color value here. So in this case we have then a scan line that moves horizontally, or we're moving horizontally along that scan line that moves normally vertically. But I guess you can see this is the very same idea. And if you look at it, why this is efficient, we need to calculate the delta x, of course. We need to calculate the 3 deltas for the color. And then we need to, so we have 4 divisions here. We need to do the same for the interpolation in between. So we have another 3 divisions, because of course these deltas here are different than these deltas here. And we have to do it, plus we need 1 delta set for the set buffer, of course. So we have another division here. But we have to do this for each edge and for every scan line, and not for every pixel. And then, so you can imagine why this is much more efficient than calculating the pixel values individually. So this is pretty straightforward. But this is then this technique that we already discussed, but now in an efficient way. And I think I didn't tell you last time that this process is called Gouraud shading, or Gouraud interpolation, if we do this with the scanline interpolation, interpolate the color values. But of course we also discussed that this gives us a shading that produces this so-called diffuse lighting, which is the lighting that you get when you have a matte surface, and then you have a light on it that doesn't reflect, so you get images like this here. But If you have like shiny objects, objects that are reflecting, then we know that they have usually these kind of highlights, these bright spots here, like with a bowling ball, a polished bowling ball, for example. You see this bright white spot, or it's not necessarily white, it's usually white because we have white light. So this, the color of this highlight spot is usually the color of the light and not the color of the material. And this is, oh wait, sorry, I'm skipping ahead. First we talk about the diffuse shading. Sorry, I'm confused. I was too far ahead. Gouraud shading. Gouraud shading is the diffuse shading, and we talked about diffuse shading before, which is the Lambertian shading. I have to repeat the Lambertian shading first. Sorry. We said the Lambertian shading is a diffuse shading. We calculate that because the Gouraud shading, I explained you how to interpolate between the values, but I didn't explain you how to get the color values. Of course, you already should know that because we talked about this when we talked about the Lambertian shading. And the Lambertian shading was basically based on this Lambert's cosine law, which says that the color depends on the cosine of the incoming light, the angle of the incoming light with the normal vector. So we have here the light source, and this is our I vector E. So we have here our I that observes our scene or looks at this particular spot, and the color at this point depends on this angle here. And if you remember, like I said, we will repeat a lot of stuff here in this second part of the lecture. The cosine of theta, the scalar product of two angles is defined as the length of one vector times the length of the other vector times the cosine of theta is the same as the scalar product or the dot product of two vectors. And that means if these two vectors are unit vectors, that is, they have the length of one, which we usually do when we model it, we make sure that the normal vector and the light vector are unit vectors. Then you see that this is is exactly the same. So we can calculate the scalar product of the vector n and the vector l, and then we have a value that is proportional to the color value at this position. So this is something that you should already know from the third lecture, but what you at that time I didn't say is, because we didn't have the perspective projection then, that we have to do this in world coordinates. So this is a little bit of a new information now, but it is pretty straightforward. If you remember what we said, that when we do the transformation with the normal vectors, that the angles are not always preserved, and if the angle of the normals are not preserved, then we get problems, of course, with the light calculation, which is why we should usually do this in world coordinates. So it is now, when we're dealing with different coordinate systems, of course, important to always know when we have to what the characteristics of these different coordinate spaces are, so we can do when we do the calculations in there. Good. Another thing that we already talked about is that this light source is only described by the direction vector and not by its location. So we model this in a way that we say it doesn't matter if the light is, for example, here or here. So the location along this direction doesn't matter. Of course, if the location is here, that changes, but that's because it changes the direction of the light with respect to this particular point here. But the position along this direction doesn't matter for how the color, or for the color of this point here. So, and this is why we call this directional light, because it only depends on the direction. And again, what you didn't know at that time, or at that time, what I said that before, but what I didn't say is that I didn't give you an example for something that is a non-directional light, and this time I say this is a spotlight, and if the term spotlight doesn't ring a bell for you or doesn't sound familiar, let me remind you that the deadline for the third programming assignment is relatively soon. Good. So now we know this is proportional to this value, but of course when we want to calculate it, we want to have an actual value, so we have to put some factors in there, and then we already saw that these factors are We use one factor to model this, which is the so-called diffuse reflection. That is the fraction of the light that is reflected by the surface. So for example, if we have a red surface or a blue surface, the light is reflected differently. That's why it looks red or blue to us, because different parts of the light are reflected differently. And this is modeled by this diffuse reflectance factor. And then we have another factor, CL, which is the RGB intensity term. That is the intensity of the light source. So this is basically the value that where the light contribution comes in. So if you have a red or a green or a white light, of course this is also different, and this is kind of modeled with this CL term. Now be careful here, this is all stuff that we already had. We use there a different notation, and that is because the book also uses a different notation. There is this simple shading model in the third chapter, in the fourth chapter, and in the 10th chapter, which is about shading, which is where I got the material from today now, they use a different notation. I don't really know why, I don't understand it. I think it's confusing and doesn't make much sense, but yeah. The book was, different chapters were written by different authors, or some chapters were written by different authors, so my guess is they just didn't update that, or were a little sloppy. And the fourth chapter is new in this edition, so my guess is in the fourth edition, then when it comes out in a couple of years, they will probably make it more equal, but yeah, for now. So in the previous lecture, I also used the notation of the fourth chapter. Now I'm using from the 10th chapter, but if you compare the two, if you just look at the slides, you will see it's exactly the same. We're just using different letters here, but the meaning of the letters is the same. And also we already had this max 0 and the dot product here, and from we take the maximum of 0 or the dot product, and the reason for this is, of course, that the dot product can become negative, and of course we don't have a negative color. We always want to have positive colors, and we use this basically as a trick to make the values positive, because if they're negative, then the value becomes 0, which means that in a geometrical sense, we can interpret this as the light source is to the back of the surface. So if the light shines from here, exactly in the same direction, we get the same scalar product value, because it depends on the cosine, which is symmetric then, but symmetric on the axis. So this is then the negative value, which is, we ignore it, and in a geometrical sense, from the geometrical interpretation, this makes of course sense, because if the light is behind a surface, it doesn't reflect on the front of the surface, of course. Yeah, so we use the normal vectors to calculate this reflection. Now the question is, of course, if we have a complex model, if we're calculating this for the edges of the triangle, and then we interpolate in the center of it, and it's pretty straightforward how we calculate if we have a normal vector in the center of a surface, how we calculate that. But what happens when we have the corners, because here we have actually three different normal vectors, because we have three surfaces that intersect here, and so we can in theory get three different color, or we will get three different color values, because we have three different normal vectors. And so the question is what to do, and it really depends on what we want to model, what kind of model we have, and what we want to achieve. For example, in this case of the cube, it might make sense that we just say, yeah, let's just use one of them and ignore the others. So each edge here, that is part of two surfaces. So for example, if this would be blue and this would be red, then we can just decide we make one of them blue and one of them red, or we alternate between them, but we just can make a decision between these two extreme values. We could, of course, also say we interpolate and use those three vectors here to calculate, yeah, it's difficult to draw in 3D, but yeah, you can imagine it, to calculate an intermediate average vector, which probably makes sense in case of the circle here, when we want to model a circle with triangles. Because if you think about it, if we take the vectors, the normal vectors here, the straight vectors, then we might get some artifacts along this line here. But if we use those two vectors here to calculate an intermediate vector, we get normal vectors that look pretty much more similar to the normal vectors that we would get if we would have an actual circle here. So in this case, probably an interpolation between the normal vectors at the vertices makes more sense. So it really depends. All right, so we also had one of the problems with this approach is, of course, if the light is to the back of a surface, this surface doesn't get any color, so it will always be put to 0, which means it's totally black. But we also know from reality, if like an object doesn't see any direct light, it doesn't mean that we don't see it, because light is reflected from everywhere. And we will see later when we talk about ray tracing that for ray tracing we recursively follow those reflections, which is why ray tracing looks much more realistic than or very often looks more realistic than this perspective drawing that we're doing here. But the problem is that this model doesn't account for this. So what we basically need is to either recursively calculate the light, or we can introduce some global illumination, and we already had, and there are a couple of like heuristics to do this. For example, one of them is to just put a dim light source at the eye position, and if you have a light at the eye and then you model everything with from the perspective of the eye, of course everything gets at least some light, because that's the light that shines from your eye. Another approach would be, and that's something we already had, to just add a constant color term to the color of each object, so we have some sort of global light that shines everywhere, and then all the light source that we put in just make it brighter than at certain positions. And this is then called the ambient shading, and you see we just add another factor here, CA, that models this ambient shading. So again, this is a new notation, a different notation as before, but again it describes the very same thing. And if you look at it, and you also, it's also important to think about, to understand what it means. So you see here we add this ambient light to the factor CR, which was the diffuse reflection. So this is the fraction of the light reflected by the surface. So of course, if we introduce a global light, then we also have to consider how this is reflected from the surface. But this other factor here, the CL, was the RGB intensity term. That depends on this particular light source. So that of course doesn't need to be considered for this ambient shading, because the ambient shading is modeled with the CA. And that's why of course we don't multiply it with, but we have this separate, and then we make the sum of it. Good, and now the Phong reflection, which I already wanted to skip ahead to. I was confused by the image. That was yeah, like I said, and here I even have the image here. So these are these bright spots I was already talking about, and in the third lecture we already talked about that we can do this with so-called Phong shading, although I have to admit I was a little sloppy there. Actually, in the third lecture we used the so-called Blin Phong shading, which is pretty much the same. That's why I didn't actually think about it. It's basically a simplification or a modification of the Phong shading, but they're pretty much used interchangeably, and also in the book. I was a little sloppy, but I have an excuse, because the book is also a little sloppy. In the third chapter they just use Blin Phong shading, and then in the 10th chapter they don't even mention Blin Phong shading, although they describe parts of it. So yeah, it doesn't really matter for you either, but of course I should be correct here. Good, so we already said that for the glossy reflection, the viewing direction matters, of course. If you look at the matte surface and you move a little around, then you see that the color at the specific point doesn't really change, unless of course you move in the shadow here, but otherwise the color doesn't really change. Whereas if you have a bowling ball and you have this one reflecting spot and then you move around, you will see that the position of the reflecting spot will actually change, or the intensity of the spot will change. So it depends on the viewing direction. And we said already that the reflection is maximized when the angle of the reflected light equals the angle of the incident light. So we have here this the surface, we have the normal vector, and we have the light vector. And then we say if we have a perfect reflection, this is the reflection vector where we get the perfect reflection, and that is the vector where we the vector that has the same angle to the normal as this light vector L. Now if our eye is exactly in that direction here, then we get the maximum intensity because this is the maximum reflection, and it gradually decreases the more we move away with our eye from that position in each direction, of course in this direction as well. So it is depending on if this distance between the eye vector and the reflection vector is small, then it also the reflection becomes stronger. So it is proportional to the scalar product of E times R. But in reality, we often don't, in practice, we often don't calculate this reflection vector, but we calculate the so-called halfway vector between the E vector and the L vector, and you see that then it is proportional to the scalar product of H and N, because if they are aligned, then we get a maximum here, and this is exactly, I think that this is exactly the difference between the Phong and the Phong shading, and so the if we use this half vector, then we see we can model this again by using this RGB intensity term and using the scalar product, and we get a color for our bright spot, or we get a color that is brighter the more directly we're looking at this bright spot. And this halfway vector can be calculated very easily based on the eye and the light vector. I think this should be pretty clear right now, so I don't have to repeat that, if those vectors are unit vectors, of course. Now, if you remember last time, or if you think about what I said with the Lambertian shading, there I put the maximum in here because I said the scalar product can be 0, and this is again a part where the book is a little sloppy. They used the maximum in the simple shading model, which is why I also had it on my slides in the third lecture, but they don't use it in the 10th chapter about shading, and but they don't they explain it there, but they don't explain why they used it before. The point is that let me just draw this here. If you use the eye and the reflection vector, then this scalar product can become negative even if the eye and the light vector are on the same side of the surface. So for example, if you look at this, if this is your surface, this is your reflection vector, and this is your light vector. This is the normal vector, which should be in a right angle. And then if you look at this is a line in a right angle to the reflection vector. Now you see if your eye vector is anywhere here in this area, the degree becomes larger than 90. And if you think about the cosine, you have here 90 degrees. So this is lower than 0. So the scalar product becomes negative even if you are on the same side, which means that with the which means you get a negative color, which is why you would need the maximum for this if you use the reflection and light vector. But if you use the halfway vector, if you think about it, the furthest the eye and the light can be away, if they are on the same side of the surface, then the furthest is this, then the halfway vector points directly in the same direction as the normal vector, so you get a maximum. And no matter how you move those with respect to each other, you cannot get a larger angle, so you will not be able to get a negative value if they are both on the same side. And that also explains why this half vector, the angle between the half vector and the normal vector is actually half of the angle between the light and the reflection, the eye and the reflection vector. So the blind Phong shading and the Phong shading are not only different ways to calculate it, they produce a slightly different effect as well. But it doesn't really matter that much because the base, it's just proportional because the angle is just a factor of 2. And I mean, this is something where we, basically heuristic to model this anyhow, because we also can control it, for example, with this parameter p that we have here, which is the Phong exponent. And I already showed you the examples here that we can use this to manipulate our bright spot here. So this is for p equals 1. We get a very large bright area here. And for an extreme case of, for example, p is 256, we get a very small bright spot. And depending on what we want to model, what kind of light and characteristic of our sphere in this case we want to show in our image, we choose this vector p, this value p appropriately. And of course, then if we use the blind Phong or the Phong shading, we get a different result, but we have to twist it and treat it anyhow. All right. Yeah. Now, if you think about what we said for the Gouraud shading, when we do the linear interpolation between the values, then of course all the values in between only depend on the values, the color values in the corners. So if we have a triangle and then we use the normal vector here to calculate this color, and then let's say the normal vector here to calculate this color, so C2, C1, and then here C3, then these only depend on this here, so we cannot model a bright spot somewhere here. That doesn't work with this Gouraud shading. So we could of course make smaller and smaller triangles, but that is not very efficient. On the other hand, calculating it for each single pixel is also not efficient. But what we can do to do this is we can interpolate the normal values, and then we can easily calculate it for each pixel. So it's of course less efficient, but it is a way to do the Phong shading even on a triangle. And the interpolation of the normal values, let me just explain to you with a simple example. If you, for example, if you have this sphere here, and let's say you have here a bright spot. Now if you take here the normal values, the normal vectors, like they are correct from the sphere, where you take the tangent here and then you calculate your normal values, then then of course we can use the Phong shading to calculate the values appropriately, that we get this bright spot here. Now if we do model this with triangles, let's draw the extreme case where we have only a few triangles. Then of course if we calculate a color here and a color here and we do the linear interpolation, we will, actually I've drawn it, let's say the bright spot is here, not here. Then you will see of course this bright spot is completely lost when we do the linear interpolation. But if we have here the vectors, we can also not calculate it based on these two, but what we could do is we can calculate here the average vector of these two here. So we have vectors that point in that direction, and then we can do an interpolation between those vectors. So we get vectors that look pretty much the same as the vectors on the sphere, only in this case they are on the triangle. And then we can use those vectors to do the Phong calculation, and in that case we are able to model this bright spot here. So remember this, probably remember this, this looks pretty similar and related to the bump mapping, where we also use this transformed field of vectors to simulate that we have a shape, a tilted shape here instead of a flat shape. And we can use, of course, also those vectors we can interpolate those vectors, and then we can do the Phong calculation here. All right, and then yeah, this is something we already saw. We can bring this all together by just adding the different models. You already saw this formula again with a different notation, but it was the same formula as here. The difference was, of course, that we didn't use, at last time we used the max, this time I left it out. If you assume that the light source can also be on the other side of the surface, then of course you should also include the max, which is probably why they included it in the book in the simple shading model, although they didn't mention anything about it. And then you, of course, you can just add the ambient lighting, the diffuse shading, and the specular or the Phong the specular shading, and then the whole thing together is then sometimes called a Phong reflection. Depending on which source you look, only that part is called a Phong reflection, or the combination of all together is called Phong reflection. That depends on what kind of book or what kind of source you're looking at. And then, of course, we can do all kinds of other modifications with this model and improve it. There are a lot of approaches to try to make it better or achieve a certain effect. For example, in the book, they mention something that we can add a factor, a term CP here, and that allows us to kind of dim the highlight of the Phong shading, so to modify the intensity of the highlight. And also we saw already in the previous in the lecture number 3 that we can add multiple light sources by just calculating this value for different light sources and then just summing it up or making an average about it. So I didn't copy the formula here, but yeah, I hope you remember it or look it up. All right. Good, so that concludes the shading part, and that actually also concludes a larger part of the lecture. So this is kind of a summary lecture today also, or was also kind of why I repeated a lot of stuff to kind of summarize it, because if you look at the book, you will see that we already covered all the basic stuff, almost all the basic stuff, with 2 exceptions. Actually, even more than the basic stuff. I think the basic stuff in the book goes just till chapter 8, which is the graphics pipeline, which I finished up today. We will not cover chapter 9, which is about signal processing. In the old edition, this was chapter 4, and I never covered that because I felt it's interesting, and depending on what you're doing, it's of course also relevant information, but it always felt kind of weirdly out of context to me. Now they moved it to chapter 9, so I think it's still out of context, but out of a different context. So we'll not cover that, but if you're interested in it, of course, you're encouraged to read it. We'll also not look, like I said before, not into chapter 3, raster images or raster algorithms, as it's called in the old book. The only thing we need from there is this the screen that the pixel is represented in the center of this grid. Other than that, we don't need it, but of course, and you don't need it to do the programming, but of course it is interesting information, so you're encouraged to read it, but this is not part of the course. We will not cover that. We will look into the other chapter which we haven't discussed about yet, from chapters 1 to 11, which is chapter 4 about ray tracing, and also chapter 12 about more ray tracing. In the old book they're combined into one section, which is chapter 10, ray tracing. So we will cover that at the end of the lecture. And in the next lecture I will cover 2 topics which are not in the book. Actually, radiosity, there is a little bit about radiosity, but I will cover this a little bit different in the lecture. Radiosity is a technique for global illumination that is a little more, less of a hack than the ambient light that we had today, so it's more a mathematical model to make a good global illumination. And then we will talk a little bit about shadows, which surprisingly are not covered in the book at all, or very, very few comments about this. All right. So like I said, this is kind of a lecture that finishes up the basic stuff, which is why I did also a lot of repetition. And I already said that in the final exam it will cover the lectures 6 to 12, but you also need the mathematics for this, of course, but those people who didn't do very well in the first exam, don't be discouraged. There are also, like you saw today, a lot of algorithms in the second part of the course, which you can learn, and you don't really need to know all or have a complete understanding of all the basic mathematics that we did before. In fact, the rasterizing algorithm that I explained today, I did this in a different way than in the book. In the book, if you read it at first, it looks completely different, but if you take a closer look, you will see that they basically describe the same thing. They just don't use the scanline algorithm and the scanline terminology, but they use the mathematics behind it, and it basically leads to the very same thing. So the people who are very mathematically skilled are encouraged to read the book chapters. The people who are less mathematically skilled are encouraged to try to understand what I explained today, and then as an exercise, try to make the relation to the more mathematical description in the book. That will help you then, of course, to develop a better understanding of the mathematics. Good. Are there any questions to the lecture today or general? No? Then let me remind you that the tutorials start again today, and let me also remind you that it's highly recommended to go there. You saw from the midterm exam that the exam questions, or a lot of exam questions, look quite similar in type and style and difficulty to the tutorial questions. And also let you remind me, there is a reason why I put the solutions not online with the exercise, but a little later, because I don't think you'll learn very much by just reading and understanding the solution, but you really need to try it to understand them, to get a better understanding of it. Also, practicals, let me remind you that we skipped the Thursday morning session from now on, because I asked last time, and also when I looked into the room, there were, except for the deadlines, of course, there were usually not a lot of people there. And the reason for this is that we are this way a little more flexible, so the next deadline will also be on a Thursday, so on that day we'll probably have an extra session there, and we'll probably have more teaching assistants there, and we have this flexibility because we skipped this one here. So this is not to save us work, but to work better for you in a way that is more beneficial for you. Good. So if there are no more questions, then I'm done for today. Nothing? Okay, good. Then see you next Thursday.